My name is Kevin Kochek. I'm the founder CEO of Chemical Q Device. Here for this is seminar, and this is episode 89, Quantum Classical Machine Learning Seminar for Medical Field. This is June 29th, 2023. So as we get more and more people kind of file in here, I'm going to split this into three pieces. So this seminar part, I have to go through, and then we'll have a little Q&A as far as do you have questions about any of these three main areas. So in specific, it's medical data, quantum algorithm, and hybrid machine learning. Now, starting with medical data, all of medical data is in classical form. This includes images, EHR data. It's the typical bits, bits and bytes that we're used to. Primary research, secondary research, meaning do you obtain your own data or you got it somewhere else. And then unstructured data versus structured data after you've done manipulations with it. You have in vivo, you have in vitro, meaning in the body, outside the body. And you have emerging fields as well. So this is fields with AI such as radiomics. So for those that don't know, radiomics is basically a bunch of medical images pre-existing, and now you treat the voxels of the images, or they're like 3D pixels, with AI. And now you have more insight into disease, those types of things. Longitudinal studies, this is all considered classical data. Now, in the quantum realm, this is okay. Classical data can be embedded into a quantum algorithm, meaning the classical data is converted to quantum data. It's an extra step, but in the near term, it's what we're likely going to be dealing with. You get theoretically less performance, and you have to watch out in some cases with the type of data, and it may affect the circuit somehow. Now, further in the future, again, all of this falls under medical data, is that quantum images, quantum data, quantum EHR, it does not exist in abundance because we can't store it. It's only for several seconds, the last time I checked, but it would give you the best performance and you don't have to embed it. You basically go straight from the quantum data into the quantum algorithm. Okay, so that's section one. So this is medical data. So section two is quantum algorithms. So I had mentioned embedding the data into the algorithm. The second step is known as a variational part, and the third step is measurement. Now, the whole purpose of using a quantum algorithm, either in a quantum simulator or a real quantum computer, is basically to get some type of quantum advantage. Now, there's two main camps out there. There's a camp that only wants quantum speedups. So this, you'll hear about exponential quantum speedups, polynomial quantum speedups, quadratic, you'll hear linear too. So this is okay, except that that's usually requires real hardware, but it's too noisy. So in my opinion, the better solution, and I just got off basically some of a ton of these lectures, and they said that focus on the physics, try to get something in the performance aspect of it, meaning that whatever's happening with the quantum bit is going to give you better loss, lower loss or better accuracy, or some other metric that's due to the information passing through the quantum bit and due to a physical advantage with it all. So that seems like it's probably the best approach right now, and especially we have GPU quantum simulators and multi-GPU quantum simulators were announced this week as well. So all of this field is advancing, right? So there's going to be better measurement. So a measurement at the end of the quantum circuit takes whatever happened in the quantum simulator or real quantum computer and converts it back into binary information, such as, so you have zeros and ones. And that's why people, that's the whole purpose, is you're trying to take advantage of quantum physics through this process of the data sliding through the quantum circuit. So it's it's definitely an emerging field. There's at least 6-7 papers in medical image analysis, binary classification, multi-class, 4-class. I was able to get up to 44-class, albeit slow. Okay, it's on a quantum simulator. So this is part two. And in specific, there's 3 subsections in part 2. So the whole purpose is to get quantum superpositioning, meaning that you have a 0 and 1, and now you have a linear combination over that, and you could do other rotations and bit flips and phase flips. This is a quantum thing, okay? And you have entanglement, which basically it connects two different quantum bits and allows for 2 to the n amount of information. So more parameters. This is in theory. Interference is a huge thing in quantum computing. In many things, it's just like if you have a sound wave or if you have an ocean wave, there's constructive and there's destructive interference. And when you have, I believe it's only quantum constructive interference, you can get additional benefit that way because that's not available in classical mechanics. You also have parallelism, okay? Now, in all these things, when you have a quantum bit, it's called expressibility. So a wide range of quantum states over a specific qubit by doing certain things. Generalizability, a broad class of problems, that's basically desired. Scalability, so larger inputs, more complexity, differentiation, say, between different types of data in the same data set. Okay, so you can start to see it when I'm in the second part here with quantum algorithms. These are the types of things that can be improved with some type of quantum manipulation, either in a quantum simulator or real quantum hardware. And of course, the end goal, and I think this is achievable, especially as medical should get more and more into R&D with this, is higher performance by math or principle. So by math, meaning this specific quantum algorithm in this spot is giving a quadratic improvement, a polynomial improvement, an exponential improvement. So also, is it taking advantage of these, superpositioning, entanglement, interference in a way that's very productive, to getting a better answer, even if we can't quite get to the point where everything's, exponential speed up kind of stuff. And then you also have, these emerging simulators, not only a GPU quantum simulator, you have multi-GPU quantum simulator. So this is to do stuff noise-free and to try to catch up, because it's to classically simulate these things, it's relatively slow. And the last part, so I went over medical data, quantum algorithms. The last part of this is basically hybrid machine learning. Now, contrary to popular belief, you cannot just put a quantum algorithm in modern machine learning and not expect to have to make some other changes. So it's the same thing as if you were to do, deep learning, machine learning classically. You have to take into account the overall complexity of the system. And if you over parameterize, or meaning that you keep changing things to the point where it's fitting the training data perfectly, and then when you go to test your test set, it's not based on a general line, then you have issues. So it's the same thing with quantum. So you have to keep in mind with these things. You also want things to try to do quantum in a quantum circuit that are classically hard to do on an inductive bias. So that's a big thing in this paper, Los Alamos National Laboratory paper, that they kept saying, is it practically useful to incorporate a quantum circuit? As in my opinion, we're starting to leave that proof of concept stage and say, okay, we really understand the nitty and the gritty. This is the type of algorithm that would, likely give us better performance. We can explain it to the nth degree better. And it doesn't increase training issues, right? So do you insert a quantum algorithm? Most of it's just it's supplementing deep learning or machine learning. It's not front and center yet. So that's why it's important to keep the R&D up with this, so we can keep putting more quantum into the operations that we're doing. Scalability with qubits, we expect to increase in qubits, not only simulators, but real hardware as well, and improves the prediction of the validation set as well. So I'm going to open this up. So I'm going to share too, I created, if you're wanting to get into quantum machine learning, I'm going to share something that's helpful. Learn the circuits, learn gates, run a quantum algorithm, and especially start to get into models, see how the classical data interacts with the quantum data. So feel free to unmute or unmic yourself. See if there's anything. Chat here. Yeah, so the national laboratories such as Argonne, yeah, definitely stayed posted, it looks like. So Ron put it in the chat here, quantum computing tutorials here. Wow. So Chicagoland's big in quantum computing, and feel free, Ron or anybody else, you can unmute or you can come on as well with video. He says Monday and Tuesday for free quantum computing tutorials, it looks like. And then, okay.
Yeah,
Go ahead,
that's
Ron.
happening as we speak. It's so tomorrow, Friday, is their last day. I didn't find out about it until early yesterday morning. So I missed the Monday and Tuesday, but I'm hoping they provide recordings of the session they had. These were basically 4 sessions a day, so a morning session and an afternoon session, and they had one speaker for today who canceled, so all that's left is what they're doing tomorrow. But it was Argonne Land. They actually had people in person, in a room somewhere at Argonne, listening to these presenters. So it's pretty cool.
Yeah, that's awesome. Chicago is a perfect example of like the people. Well, it's same. If you have a quantum computing hardware manufacturer in your city, chances are other people are going to get involved that aren't even related with the company, right? It just spreads throughout the public. You're at a grocery store, somebody mentions quantum. as something as simple as that. Now, Argonne and same Fermilab, I might fall a little bit closer. They've done quantum internet stuff. They were the first to transmit quantum and classical data at the same simultaneously over the same line. And I can't remember how close they are, but they're in the same kind of vicinity. So it was a good kind of cool thing to see, and that might have been over a year ago, but I think it was 2022.
Yeah, Fermilab is not too far from Argonne. I wish I would have known about this thing. I could have drove down to Argonne, but
Yeah, and
maybe for one session it would have been cool.
I mean, you have those two. I think there's over 13, something like that, over 13 national labs. Another one I follow, and I'll put it in the chat here in a little bit. Los Alamos National Laboratory had some of the most practically useful quantum machine learning how-to articles out there. And one of them is challenges and opportunities in quantum machine learning. The other one is like something like subtleties in training hybrid QML. So the links I'll share a little bit later, they both have that. But yeah, stick close to the experts and watch a lot of the YouTube videos, read the papers. If you have a hard time reading, do text to speech. Sometimes works. So awesome. Anybody else? I saw we have another startup here. So Samuel said Cubra, so startup in Brazil. And feel free if you want to unmute or you can come on as well. You could also post in the chat. And I'm not quite as familiar with the specific startup. And then I see we have some other people here. So Ionis or Thomas, feel free to come on. And then if not, so Mo or Hallie. And again, so what was covered is medical data, what types of medical data, quantum algorithms, and the incorporation into hybrid machine learning. So, if you're big into machine learning, so there's also a book in the chat here too. It's like on Amazon. And it's the type of field, it takes a lot of hard work. It's a lot more than I thought, but just if you do the tutorials and the demos and change them in a way that it's improving them, then you could start to understand. And if you have a machine learning background, all the better, especially Python too, because some of them aren't like super deep learning or super machine learning like the Qiskit ones typically. But it helps to kind of like work through a lot of that. And feel free. So Edwin, Edwin or Samuel, if you have any questions or if you want to come on.
Oh, yeah. Yesterday I attended this webinar by UK Quantum, and it was about standards by some person called John Devaney. And yeah, saying quantum needs standards. He's from the National Physical Laboratory. I think it's British. Yeah. So yeah, there's that some standards, and people are kind of lost. Some people asking, where do we even start? Like, are there even guides? yeah, but it was interesting.
Yeah, I'm glad that you brought that up because IEEE, they have, I think, at least 10 quantum standards, and I don't know at what stage, fully developed. Obviously, we don't have quantum computers approved by the FDA yet. And then the other one is ISO and IEC. They just did a 50 approval on quantum key distribution. So there's two of those. And that's kind of like our front runner is those algorithms. And actually, I believe they're classical algorithms. People call them quantum, but you don't need a quantum simulator. You just run them on a regular laptop, but it helps to defend against quantum attack. So yeah, quantum cyber security is definitely a huge thing. And it's the front runner because people don't want their information stolen. It's pretty simple. Like it's the fear of a different country having a better quantum computer, basically. And then anything else, Edwin? If not, I saw George. Feel free to unmute or unmic. You can come on as well. And then we are having some demand for the other startup here. So Samuel, feel free to come on. Okay, he says QML for education. That's awesome. I'm glad you found this meetup. That's part of it, right? Because it's not fully known, right? Like all of the people that you're trying to impress they don't know about quantum. So what better way to educate? But yeah, feel free to, if you want to share, you can come on as well, Samuel.
So I can share, I finished a paper by one of your past attendees, Kevin, Dr. I'm going to mess up her name, Dr. Imine. Do you remember her?
Yes.
She published a paper on quantum support vector machines. I got through it. It's a little bit sparse. Although I think I've got a good understanding of what how they went about it, but it doesn't include any code or any links to code. It doesn't include a link to a quantum circuit, although there's a diagram. So I'm going to keep moving forward on that. I know there's a lot of papers out there, but I found it very interesting in this particular attack on support vector machines. The way what they did is they used a quantum algorithm to compute a kernel function. So using a kernel function is a classical way of enhancing a support vector machine. It allows you to project your feature set onto higher dimensional space. And the nice thing about it is because the function does the projection and then it does its calculation, once that particular calculation is done, they don't need the data anymore. So the cool thing about that is you don't need to store those dimensions anywhere in memory. The kernel function just handles it. So and the more I looked into it, I'm starting to realize that is probably one of the coolest ways I've seen quantum being used, because quantum is so good at optimization issues, and that's really what's going on, is trying to find the best optimization for the coefficients of the projection onto the higher dimensions. So hopefully, as time goes on, I'll have more to report on that.
Yeah, that's cool. The treasure trove that I found is through GitHub, and in specific, it's the Penny Lane Quantum Transfer Learning demo. And then people have done BERT Quantum Transfer Learning, which is basically like a text version of Transformers. It is a Transformers. And I haven't had time to go through that one, but they've done kind of CNOT studies, like where does it help to have these entangling gates and quantum transfer learning, and where does it hurt? So again, a lot of this is just like backlogging for me because I find it and it's just like I have other stuff to do. But yeah, that one in specific has a ton of code, full models. They should work and you can run them. I'm trying to get a transformer, a VIT, which is vision transform, which is images with transformers. And I got the classical to work really well, like close to 100% for training. But it's some issue with outputs and that kind of stuff. It's blending that. So that's why I want to try to learn from Bert and then, go over for that. And there's actually, if you remember Brand Raw, he presented on Bert maybe 30 or 60 episodes ago, a while ago. And it's an important field, transformers, better, but typically better results, especially as you increase parameters that it was trained on. So, okay, so here we go. So Samuel says 2024 start to do activities focused on research. Okay. And then he says amyotrophic lateral sclerosis in a hackathon. We're aware of the challenge and complexity of subject. Okay. And okay, the author sent me. And feel free. So anybody that we haven't heard from, so Mason or Thomas or even Mo, feel free to come on. And it's fine if it's a completely general basic question. That's fine, right? Because it's data, algorithm, and then you have the model, which is a hybrid model. So, and if you have a sort of quantum, I put some stuff in the chat there too. So definitely know what quantum gates are, the circuits, run some on real quantum computers and simulators, and then you want to wind up at models because models are the where you're doing an application of it all, seeing if it should be slower, if it's a quantum simulator, if you're getting better performance, inserting quantum. And yeah, so Hallie or Ionis? So feel free to put anything. Go. Is that somebody?
Yeah, I was viewing this some post on some news about a startup called Molecular Quantum Solutions, and yeah, they have some tools that they are converting to a SaaS solution that can help. I think you talk a lot about molecular quantum solution, then they could benefit a lot the pharma and chemical industries. So that was really, really nice.
Yeah, a cool company to focus is Shahar Keenan is the CEO of a company called Polaris QB. And so her startup just posted this thing of it's a specific thing, and it's kind of like what somebody else is saying. It's like you're looking for a better, you're funneling down for drug targets for this specific thing. And you always want to talk to people too, because there's much that can't be included in a PR newswire, kind of thing. But yeah, her company, Johnson Johnson, Meten AI, Menten AI, they're all in that arena of using quantum to the best of their ability to get some, better results, basically.
Oh, that's cool. That's cool.
So you're typically at this stage, if you have a lot of data, you can do, quantum annealing. And in certain cases, even if you have some noise, as long as your results are better, I think, than classical, you're getting somewhere, right? Like it's that whole uncertainty. If you have noise and you have patient data, somebody live at the table, I don't think we're quite there yet. But yeah, so she was saying it's a lot of approximations and 2D. So if you have 3D molecules, you might flatten them into 2D space. So to do these kind of quantum operations with gates, I think they mostly use annealing, quantum annealing, like D-Wave, is that you have to, you can't go to the full effect with it all. But it sounded like it's productive. And there's at least, I think, 10 companies that are in this kind of field. So drug discovery, quantum AI. Many people will remain silent until there's some other big news, and it's hard to tell where everybody else is at. Yeah, so Edwin, so it's IEEE. So if you search for, it's IEEE. So if you search for IEEE quantum standards, it should take you to that page. And then at the bottom, you can open it up, and you could see it's their software, algorithms, hardware, those types. But I know for medical, like FDA, it's not IEEE, it's you have to have IEC or ISO, ASTM, NEMA, and I think those are more on the medical side. So I think the ones that IEEE ones are kind of like a head start. I don't know who requires IEEE for standards for certain things. And there was a law back in December that requires federal agencies to implement quantum cyber defense. So that's important. That's President Biden law. The quantum computing is a government initiative. It's not industry. It started like early 1980s with NSF funding. And then anywhere from the NIST, the 4 NIST quantum algorithms that are working their way to 100% usage, to NSA, to NASA using quantum annealing up in space for communications. It's definitely, it's a government initiative, but the industry has helped it a lot. And I think between NIST, DOE, NSF, that's over $800 million per year the past 3 years. So it's a lot of funding, and they're very aware of quantum. To get to that point, you just understand the basis of quantum is it's a different nature, right? So you can do certain things with quantum bits that you can't classically, and vice versa. So when you're trying to accomplish a task like separating data, you really want to have a fundamental understanding that if you use this type of embedding layer, that it has a tendency of separating data better, and your results will likely be better than classically. So, many people want the quantum speedups, right? That's a huge thing. But a lot of people, and I think it's sometimes to the back burner, is focusing on the physics of it and saying, okay, well, if we understand X, Y, and Z, then we should have this quantum effect. And by the time we measure and it goes back into classical information, that there should be a significant benefit. So, so Samuel asks, is there already any research focused on the use of QML in decision-making by medical robots, such as those used in surgery? No. And to be honest, I struggle with figuring out where AI is exactly used, because you look at companies like Viz.ai, Subtle Medical, AI Doc, and I know they're using AI for that. And then maybe for the smaller hospitals, it's not to the nth degree. But a lot of that is still going through legislation as far as the amount of AI in medical and other fields too. So as far as I know, I haven't seen anything where it's gone past. We're in the research and development phase. We're not there yet, I think, with quantum mechanics, even quantum simulators or quantum annealers in healthcare yet. But it's a field that should be researched, right? And, even if you're not getting this theoretically awesome quantum speed up, there's so much to research as far as like, if I do this with a quantum bit, if I rotate it here and a bit flip here, and then my data goes like that, and I can, keep experimenting with it. And most often your experiments don't work like you want. Like I was up later last night trying stuff, but it was based on papers, right? So it depends. It depends on your data, your application. Sometimes it's just luck, but you'll increase your luck if you read more papers, kind of thing. So that's just what I found. But yeah, that's the hope. Is deep learning and machine learning is a bigger jump in my mind than inserting a linear quantum algorithm into an existing, machine learning model, because machine learning and deep learning is more like learning from data. You're really trusting the quantum or the computer, the classical computer. And then for the quantum algorithm, it's more like it's converting it into, quantum data. It does a manipulation and then it outputs. It's not quite as complex as their most, your ResNet 34 or your transformer, VIT B16, those types of things. So, but it's a different nature. So people will have to trust it, especially if it's going to be a quantum simulator. Is it going to be, can we use quantum annealing? How long is it going to be for, say, like an ion trap or neutral atom quantum computer, those types of things. So it's difficult in anything to get a good consensus. But I will tell you this. So IBM Cleveland Clinic, they have a 10-year deal. It includes quantum computing. So IBM just put the first quantum computer into healthcare at Cleveland Clinic. Somebody had asked about the cybersecurity data. Sandbox AQ, which is a Google spinoff, they have a partnership with Mount Sinai to address patient data security using some quantum tactic. You could read the thing. I didn't get much more than that. NYU Langone, which is a hospital in New York, combined with Fermilab, is they're working on a brand new MRI analysis with quantum sensing and quantum computers. I don't think there's been much since that was a last year publication. But if you have quantum data and they can store it for days or say 30 days, and you don't have to embed it, those types of things. So there's the bigger hospital systems are involved with quantum. Okay, so Edwin, so I'll put it in. So it's basically QTL, or if you type in, this is for Edwin. So quantum transfer learning, and then just type that into GitHub, and there should be a bunch. Like I said, the coolest ones I found were the BERT QTL, and it seemed like it was done pretty well. And kind of like there's a comparison of using entangling gates, and there's much research on a lot of this. So anybody that we haven't heard from. So if you came on a little bit later, that's fine. So let's see who we haven't heard from. So Hallie or George. And I put out a little survey this week asking people what in their opinion needs to be changed with medical AI. Not even mentioning really quantum, but just something for me to keep in mind. So feel free to answer that question on your own right now too. Or you could share it with the group as well. So I'm trying to think basically stick to the code, right? Like GitLabs, find something to work on, right? That you can spend some time on to change the circuit, right? Change the gates. I spent a lot of time hyperparameter tuning just the quantum classical model, which is more classical because they're classical algorithms. And it's hard, right? If you don't have a machine learning background and you're dealing in these environments. And you heard me say it, I think like 2 weeks ago, that people that finally believe in quantum machine learning and in specific quantum algorithms, and they start to jump on quantum algorithms, they know how to put it in their notebooks, then you're going to see, because there's so much you could do to improve, based on regularization and dropout. It's such a built up industry with machine learning, I would say. And then feel free, so if you came on before, you can come on again. So Ron, Samuel, if you have anything else regarding the startup, and then you can share any links. Always a cool thing. We're kind of in this together to a certain extent.
Another area I've been seeing a lot of application of quantum in the medical field is genomics. Yeah, I've been seeing a lot of articles on that, especially on Archive.
Yeah, you're going to see a lot of it. I mean, I think because they refer like imaging and clinical data, those are kind of separated. Genomics, I'm not quite sure if that's typically considered EHR data. Imaging typically is known to take 90%, and then everything else is 10%. but Edwin, and this goes for everything else too, is, and Ron was kind of mentioning this earlier, is you have to find the specific cases where it makes sense to experiment with quantum algorithms in that specific things. Because there's many things that could not work, but there's, say for instance, if you think you have a polynomial speed up and based on, you examine the workflow of genomics, insert the algorithm there, see what the results are, those types of things. But a lot of the times it's educated guesses, right? A lot of the kernel work. So this is like kernels, quantum kernels, kernel trick kind of stuff. And at LANL, or the National Lab, they call everything else a QNN, but it's typically it's a classical algorithm converted into quantum, or it's a PQC algorithm. Okay, so I think the field, in summary, is it still needs a lot more explored. There's a lot of like, usually you don't come across something right away. You really have to say like, okay, well now it's this combined with this, and then you see what I mean. It's not like a straightforward kind of thing a lot of the times. A couple people to follow: Seth Lloyd. I put in the chat, there's 2 LANL papers, and there's another paper that had to deal with embeddings. So that's good to follow. And embeddings are probably the most important thing right now, to be honest, because you can go wrong really fast with the wrong embedding, meaning that to transfer quantum to classical to quantum is really important. There's new measurements coming up called Hellstrom, and I think you can do them, but like with data, it's hard to do computationally. HELSTREM, so Hellstrom measurements, those are coming up. IQP, so if you need to use instantaneous quantum polynomial for your embedding, it has entanglement, but it's typically more computational demanding. But I've seen people use it, so IQP for embedding. And, the list goes on and on, right? So it's like you could get decent results and they say, if only we could do this, but we're limited in simulator or hardware kind of thing. So hopefully this will be an awesome summer, for development. Grab a research project and then keep working on it. Did you have something, Ron?
Yeah, I would follow on to what you were saying. I think there's a lot of misunderstanding out there in the, like, especially the classical community. You'll hear people talk about QML or quantum machine learning, and it is never going to, it's not probably ever going to be anything that's a replacement, like a drop-in replacement, like if you've got a machine learning stack, there's never going to be a version of it that's the whole thing is written in quantum. It just doesn't make sense. And even if you could do it, it doesn't make sense. So what QML really means is there's pieces of the machine learning stack that can be implemented with and exploit the quantum advantage. But for right now, like what I was explaining earlier about the support vector machine, you're using a classical support vector machine. All you're doing is you get to that point where you need to start the training process. You call a quantum algorithm to get the coefficients for the kernel function, and just that simple thing, from what I'm seeing, is being shown to speed up either your training processes, requiring fewer epochs to train, getting your stack to stabilize faster. And there's also potentially the same type of technique can be used to speed up the inference engine. But again, it's a hybrid, and it's going to be a hybrid, and that it's going to be more slanted to classical for quite some time. And like I said, even if you could write the whole thing in quantum, it doesn't make sense to do it. Quantum isn't very good at doing things that classical machines are good at doing. things that classical machines do well, quantum isn't that great at it. Quantum accelerates at attacking the intractable problems, the things that classical machines don't have algorithms to attack. That's where quantum steps in. So I see in the chat that people are asking, well, what about QML for this or that? It's like, there isn't going to be a QML version of a particular ML model. There'll be quantum techniques that are plugged in strategic places on existing ML models.
Yeah, I mean, the closest I've got with this is just understanding literature better, because the main type of math quantum is linear algebra. So if you have a deep neural network or something like that, that's typically not linear, but quantum is linear, that's thought to be a restriction for that point. And yeah, I mean, it could be many things that you have a quantum algorithm that can do this, say, for instance, like, help out with epochs every time it passes around. But yeah, it's typically, it's quantum assisting machine learning. It's not like quantum doing, in specifically a convolutional neural net, that's learning curves and these types of things, or even a transformer. Like there is no, like a quantum transformer, right? It's a quantum algorithm after it passes through all of the, like, your vision transformer or whatever, and then it changes the data in a quantum way, right? You have a qubit. And it really, like, if you have, like, simplify it, there's a book by William Hurley. It's called Quantum Computing for Babies. And it's that simple. Like, if you can understand the little things, like if you have a data, a bit coming in, you have a superpositioning. So now it's not 0 or 1, it's a complete linear combination over the quantum bit, right? That gives you an idea. Now, if you rotate it like a RY, RX, or RZ, you're just turning it, right? So I just described the Hadamard gate and an RY or RX, RZ. And then you can do an X gate, so that does a bit flip, or a Y gate, which is bit and phase flip. Those types of things, right? So that helps a lot if you can understand the very simple things about quantum. And it can get confusing really fast if you're pulled in all these directions. So that's my recommendation, is find a really good, maybe a shorter book to start off with, just to kind of break it down. I think Ron has shared before in the chat, is basically there's these, guides that can take you through, but only get one that you think that you can finish, right? Maybe in a week or two, because you really want to start running. But if you have an understanding of kind of like the coolness, right? This is a quantum realm. Every simulated qubit is not physical. Okay. Every real qubit in a real quantum computer is physical. So it's kind of cool that you can almost perfectly or perfectly simulate a quantum qubit in a classical computer, and it's noise free. It's slow, right? Because you imagine a linear combination over 0, 1 for a quantum bit, that takes a lot of RAM, like GPU RAM kind of stuff. But it's a cool world, and I would get hooked on that. Like, quantum computing is cool. I got hooked more like on the headlines at first, and then you kind of work your way into it, and then all of a sudden you can start to feel like, hey, I have the potential of coming up with something cool. Awesome. Anybody else that we haven't heard from? So kind of curious as far as like the whole, quantum AI, medical, these types of things. And there's a reason for using quantum, right? Superpositioning, entanglement, interference. I would understand all those pretty well. And there's tricks too, without getting too far into it. But a cool paper, I came across 2 cool papers. There's an MIT paper that did an entanglement study, basically. It's called the HAN Lab, HAN. And they found that this specific quantum algorithm, even though it didn't have C-naught gates, which are, for entangling, perform better in entanglement capability than all these other bigger quantum algorithms. And that circuit that they call is called circuit 1. And then I've been experimenting with it. It's for specific. It doesn't seem to match my specific application, but there's cool stuff like that. Like you just come up. They must have just stumbled across that. It's just an RX RZ gate, and it beat all the other big entangled circuits. So it's not always intuitive, especially because bigger circuits, higher compute costs, those types of things. So that's that one paper. And the other one I came across today, it says the exact compute cost of a Hadamard gate versus an X gate versus a C0 gate, Toffoli and Fredkin. And it gets way up there, right? Like if you're trying to do really fancy stuff. But I'll tell you one thing, a lot of times in the area that we're in right now, the smaller quantum circuits, if your understanding is correct and you're applying it, a lot of times they don't have to be that fancy. They're not these highly entangled circuits with many, many C0 gates, those types of things. So, and you can find all that in literature. Go ahead, Ron.
So I have a quantum experiment that everybody can do. Okay, so go to Amazon and search for quantum computing books and then sort it by publication date. So what you get, if you do everything right, is the books that'll show up first are the ones that are in pre-order mode, which means they're pending. They haven't been released yet. They're pending release, but you can pre-order them. And just go count how many there are. About a year or so ago, I think I counted almost 100. So it'd be interesting. I'll have to go do this myself and see where that number is at these days. Along those same lines, if everybody is familiar with the publishing company Not for Dummies, like Windows, for Dummies, Not for Dummies, like Windows for Dummies. Of course, Windows is for dummies. They are going to they're in the process of releasing their quantum computing for dummies entry. So lots of good places, lots of good material will be out there, but there's a ton of free stuff you can go and find. If you're just starting, go do the Qiskit tutorial at qiskit.com. Great place to start, and it's free.
Yeah, I appreciate that. Like, it's definitely worth researching. I'd mentioned Seth Lloyd. There's John Martini's. Now, John Martini's, his first paper was the month that I was born, April 1983, and it was on squids, actually Josephine junctions with quantum. And then he worked his way up. He was the Google quantum head for the first quantum supremacy back in, I think it was October 2019, and it was published in Nature. Okay, so every once in a while he comes out of the woodwork and it's a big quantum announcement. So that he has a web page, I think it's like Quantilla, something like that, but it's spelled just like the drink, I guess. So John Martini's, Scott Aronson. I was just watching a lecture with 4 other quantum experts, and he's the head of a lot of these UT Austin researchers, so University of Texas in Austin. And he came up with a book. I don't know if anybody else, it's kind of a humorous book related to quantum computing. And I can't really recite the whole title off the top of my head, but if you search for Scott Aronson, even on Amazon, I've heard other people kind of recommend that. Now, I've never brought up this gentleman, but you could check him out. He's a unique individual. His name is Bob Koch, Coecke. He works for Quantinuum, and he came out with quantum spiders. So I think it's part a way of learning quantum and also kind of like some more in-depth stuff. And he's very interesting fella. He runs teams in quantum, so he leads some things, but I would say he's a little bit less conventional than other quantum researchers that you might see. And Maria, what's her last name? She works at Xanadu. So she's kind of actually a lot I learn is from Penny Lane, Xanadu, this whole team, and they've collaborated with MIT with Seth Floyd. So yeah, so a lot of the things they say you might not even need this part of the circuit because this other part of the algorithm is doing this, say for instance. So there's a fair amount of experts out there, and it's good to kind of like, see who keeps publishing on something that you're interested in. So that'll save you some time too. So yeah, Edwin put the Qiskit textbook. That's awesome. And then Penny Lane, yeah. So there's no shortage. If you're trying to do something, there's no shortage. Usually you'll run into like a hardware, we don't have it, or the simulator. Although a multi-GPU quantum simulator is going to open up some pretty awesome areas, in my opinion. Certain parts that would take, say for instance, if it's multi-GPU. Now, NVIDIA has run, I think, close to, if not over 800 quantum bits on say like 1100, let's see, 1100 GPUs. Now that's not mainstream and that's not practical because I don't think a multi-GPU goes up that high. But there's been some studies that kind of perk your eyes and it's like, if I had 800 I'm looking for 88 qubits for 44 classes right now. And, sometimes you have to wait. Awesome. Anybody else we haven't heard from? So Samir, I saw you joined here, and then it could be strictly quantum or strictly medical. That's fine. Yeah, George, and then the other gentleman here, the FVA. Feel free to. You can either come on or post in the chat. This is definitely an ongoing discussion. I would say a lot with quantum.
Yeah, I just came out just now, but I'm not sure how that works very well. Sorry, I missed the beginning.
Yeah, and if you're coming from machine learning or medical, it's basically, so there's three main parts. You have medical data, you have quantum algorithms, and then you have the hybrid model. So those are the three pieces that come together. So the medical data, most of it's classical, so it has to get embedded into a quantum circuit. And the circuit is the container for the algorithm, by the way. And the quantum algorithm inside it, you can change, and you're taking advantage of this quantum mechanical world in a real quantum computer or simulator. And then hybrid machine learning is more like fine tuning. So similar like you would in, machine learning, but now you have to figure like, does the scale of the quantum circuit match this, the scale of your classical, pre-existing, those types of things. So that's the main gist of it. And there's two camps. There's we just want better speed ups, and others that, or maybe three camps. Others that say like, oh, okay, we just want to get better performance based on the physics of the quantum bit, right? That will separate the data better in a way that we haven't done before. Or many people might probably want both, right? Speed up plus, better results kind of thing.
So it has the potential probably to speed up the algorithm, ML algorithm, to the point that even if you have extremely large data sets,
yeah,
you can get very quickly.
And especially in the near term, in a very specific way, right? Because it's only going to be used. The two mains are known as quantum kernel and QNN, or quantum neural network. But yeah, in a very specific way. So I would say the speed ups, like even if you have a mathematical speed up and you think you can use it, it's exponential faster. You're limited by quantum simulators. They're slow, and then the quantum hardware is probably not going to be there. It's just too noisy. So that's why I'm saying these days, that's what it makes sense to maybe use quantum simulators and then get the performance, like the better accuracy or lower loss. That seems more near term, but it's gonna, even if it's a faster algorithm, because it's simulated on a classical computer, but then if you have a GPU simulator or a multi-GPU, it could try to speed that up, but it's not, you're not apples to apples with classical anymore, right? Because then you can use a multi-GPU, whatever classically. It's just so it runs good enough and you're getting that performance. So yeah, it's a developing field. But yeah, Penny Lane actually, so Penny Lane is probably the biggest after reading a lot of these papers. It was the first quantum machine learning. And I think it came out a lot earlier, like a year or two earlier than Qiskit's QML. Although Qiskit came out before Penny Lane is typically for quantum machine learning. So they announced a new, not episode, but a new software package, so, something like 30.1 or something like that. And anyways, stuff with qtrits. So if you've ever run, they have a qtrit let's say default.qtrit. So a qtrit is basically, instead of having zeros and ones, now you can have 0, 1s, and 2s. And it's certain things like say a triple entangled gate, like a Toffoli gate or Fredkin or something like that. It might make sense to use qtrits and then convert back into binary. But you can't. Anyways, they announced additional support for qtrits, which are quantum trits instead of quantum bits.
Yeah, I'm seeing the book that George has just detailed there in the chat, and also the discussion that or rather the challenge that Ron has just given about going to Amazon. And I was visiting Reddit the other day, and there are these groups on quantum, and there are some really nice discussions there. Actually, some people are saying we're talking about the book by another book by Nelson called Quantum Information and Quantum Computation. Yeah. So it's a place. I think it's a nice place to go chat and see what others are saying.
Yeah, that's it's not really a book, it's a paper that it's people refer to it as the Quantum Bible.
Okay.
If you hunt around for it, you can download it for free from a number of colleges and different repositories. It is very math heavy.
Okay.
Yeah.
Yeah, it's almost like have a goal and then work backwards, right? Like think what you're trying to do. And you might need a mini goals before that. Say if you'd like to improve a IBM and whatever Penny Lane model that already exists, like you outdo the authors. That's a good goal. And there's so much, I mean, you're not going to get, and because you don't have the math background or you don't have the time. But help listening to experts. I was listening to this is a 2021 Future of Quantum Machine Learning, and it had Maria from Xanadu. It had, let's see, Haro. Let's see, Aram Haro. So if you know the HHL algorithm, so his last name is in that algorithm. He's an MIT researcher. And it had at least 2 other people, one lady from Ewan from UT Austin, and then another gentleman, who he worked for. But anyways, it'll get you like in that frame of like, okay, this is what I should go after, right? Like I had to rewatch it twice. So watch it like 3 months ago, something like that. But if you stay closer to the experts, the people that publish a lot, you have a greater chance of doing something that's kind of more effective, as opposed to just kind of, randomly changing your circuit for no reason. But sometimes you can come across things, especially like I had a bigger algorithm that ran better than the smaller algorithm. This is in Qiskit on a real quantum computer. So that's not common, right? So I was doing things, I kind of knew what I was doing. So like a Bell state, I did a modified Bell state algorithm. Awesome. Anybody else we haven't heard from? You can come back on, Samir. So if that helps at all, as far as like how you could use specifically quantum or Thomas as well.
Yeah, I think I appreciate that all of the information. I'm in more of the classical side of things right now. So for me, this is kind of like a learning point to kind of, dip my toe at this point and then kind of figure out what do I need to be reading? What do I need to be kind of looking toward? Because it seems like every month I keep getting pushed a little harder and harder to kind of
Yeah.
do more and more. So I'm looking for an edge.
Yeah, if you're looking for an edge, definitely find working models, at least 3 of them, just run them. And then, at that same time, kind of figure out what would be a good adjustment to make on the quantum side. And then do it, see what the results are. If you get better results, then that's a win, right? A lot of times they'll just have an algorithm, an H, rotational gates, and then C knots. That's like a standard algorithm, but you don't always need the C knots, and then you can change the rotational gates. And I mean, you can really get in depth with having a quantum circuit that's to a specific sine wave that's supposed to fit the model better. And that I actually was running this algorithm. I did that, and then I found out that that was the correct one anyway, but it was based on anyways, a lot of times in the model, they'll have the correct gates. Other times you have to remove some, it just depends. But if you get to the point where you're running and you can make, focus on the quantum, make changes that would either, should make better performance or decrease time. I did some work, certain types of gates or circuits will run linear in RAM and runtime, as opposed to other ones like CNOT gates are exponential, right? So there's a lot of resources to get started, I would say.
All right, thank you, sir.
Yeah, anybody else? Any other last questions or comments? Appreciate everybody coming on. So this has been episode 89, and this is focusing on hybrid quantum machine learning, medical data, quantum algorithms, the purpose of it. I hope that you were able to get a better understanding of like the difference between, especially with quantum, run quantum here, it makes a little bit more sense, and then do your research and development. I appreciate everybody coming on. Have a good rest of the night. Have a productive rest of the week. Take care, everybody.